Hey there, how's it going? So we're going to talk. We're going to talk about binary conversion from binary to decimal. And so I'm going to show you two things. First of all, I'm going to show you kind of the math piece of this. In other words, what the mathematical basis for this is, and how you would have learned this if you were learning it in a math class, as opposed to in a computer science class. So binary numbers obviously are base 2. Meaning, unlike our normal numbers, base 10, which have 10 possible values, 0 through 9, in any one place. Binary is base 2, so only 2 possible values, 0 or 1, in any place. So if you have a number like this, right, that would be a binary, that's in binary. It's not 11,011. So what is the value of this if we were translated into binary numbers that we're used to seeing? So here's how you would determine that. The math class way of determining that. Well, what you would look at is you'd say, well, each of these is a value of 2 to a certain power. In other words, this first place is 2 to the 0 power. This is 2 to the 1 power, 2 to the second power, 2 to the third power, 2 to the fourth power. That's the way that they would view these things. So 2 to the 0 power, anything to the 0 power is 1. So the value of this first digit is 1 times 2 to the 0, which is the same as 1 times 1, which is 1, right? This next value is 1, because there's a 1 here. Of course, there can only be a 1 or a 0, right? Times 2 to the first power, which is the same thing as saying 1 times 2, because anything to the power of 1 is just itself. And that equals 2. It's 0 times 2 to the 2 squared. So that's 0 times 4, which is 0. Here we have 1 times 2 to the third power, which is 1 times 8. And 1 times 2 to the fourth power, this last digit here, this highest digit here, which is 1 times 16, or 16. Then you add these all up, and it comes out to 27. So in binary, it's 11011. In decimal, it's 27. That's how you would do it mathematically, because each place represents 2 to a certain power, right? I mean, we don't normally think of our decimal numbers that we're used to working with that way, but they actually do work that way, right? If you have 1,246 things, right? This is 6 times 10 to the 0 power, right? 10 to the 0 power is 1. So this is worth 6, right? This is 4. This digit here is 4 times 10 to the second power. 10 to the second power is, I'm sorry, not to the second power. 10 to the first power, which is just 10, right? So the value of this digit is 40. This one is 2 times 10 to the second power, which is 2 times 100, right? So the value of this digit is 200. So, our decimal numbers work just exactly the same way, except that it's powers of 10 instead of powers of 2 that we're working with. So that's the math way of viewing binary numbers and working with converting binary numbers to decimal. But that's not the way we really do it. That's not the way I do it in computer science, because in computer science, we're almost always most often when we're dealing with binary values, we're converting a whole byte, 8 digits. So the way I do it is I'll draw up here an actual set of boxes for the byte that I'm going to be working with. Okay, so I'm working with an 8-digit binary number. Okay, so say that number is, and usually I'll put zeros, a slash through my zeros. because it just makes it easier for me to be sure we're clear that they are zeros and not O's. In the computer world, we tend to put a slash through a zero so that you don't confuse it with the letter O. So this will be a byte, and I represent it this way because it's easier for me to work with it this way. So the value of each place in a byte, it's pretty easy to just remember. This is something you just kind of have to memorize. It's not hard to remember. These are the values of each place in your byte. So all you have to do is, if there's a 1 below it, then you have that value in your byte. If there's a 0, then that value isn't there. So for each one, you just write the number if there's a 1 in its spot. Otherwise, you just leave it out. Right? If there's a 0, right? There's no 8s, but there's a 4. There's a 32. There's no 64 because it's a 0. And then just add all of these up. Right? That's not too hard to do in my head, right? 128 plus 32 is going to be 160. And you can actually write each one down here if it makes it easier for you. You can just add them a little at a time. 160 plus 20, and that's going to be 181. Right? So not too hard. And that's how you're going to convert a single byte into a decimal number that you want to represent. If you can do that, then you can do any of this binary math. The next challenge comes when you're having to deal with, like we're going to have to in our IP headers, we're going to be dealing with some values that are 2 bytes long. So you have 2 bytes that represent one number. And so you're not just dealing with with 1 byte that represents one number. You're dealing with 2 bytes that combine for a number. So it's a 16-digit binary number, 2 bytes long. And so I'm going to show you how to do that in a moment here in the next little segment of this video. Okay, so we talked about doing 2 byte values. So let's give an example of, say we have a 2 byte value here. I'm going to try to make sure I have enough space. So these are going to be a little smaller. I always divide it in half first because otherwise I end up not being very neat. Once I have it in half, it's easier. So then put 3 more lines in each half. And so here's my 2 bytes, right? And they're the same as before. Each one has the same values. And that's the key thing to understand. Each one is, for the purposes of how I do this, each one is still a byte. All right. So one way to do this would be to treat this as all one big long value and say this is the 128th place, this is the 256th place, the 512th place, the 1024 place, and so on. But that's actually not the easiest way to do it. The easiest way to do it is to do them as 2 separate bytes. So say this is our value. Okay, I just kind of randomly threw 1s and 0s in there. It doesn't really matter. So for each one, we're going to do the same thing we did before, right? If there's a 1 in that spot, that value comes down, right? So you can add these up. That's 16, 24, 26, 154 here. So this byte here is 154. This byte here, we've got a 2, 8, 16, 32, 128. All right, so this is the same. The only difference is we have a 32. Otherwise, it's actually the same. I guess my random choice of 1s and 0s is not as random as I'd like to believe, because they're actually the same except this one has a 32. So it's going to be 186. All right. So this byte is worth 186. This byte is worth 154. But because both bytes together are one big value, like we said, really this is the 256 place. So the value of this entire bit, of this entire byte, that is whatever its value is, times 256. All right, now obviously you can use a calculator to do that. But just to prove that you can do it without a calculator, it's not that difficult. I'm actually just going to go ahead and do it longhand on the board here. Okay, so 6 times 6 is 36. 6 times 8 is 48, which is plus 3 is 51. 6 times 1 plus 5 is 11. All right, so that is the value of this byte. So this byte, like I said, this is the value of just this one byte, but since it's what we would call a second order byte, it's the higher byte. The actual value of this byte is its value times 256, so it's that. And then if you want the value of the entire number, you've got to take that and add the value of this lower byte. And there you've got it. This is going to be the value, I didn't put a slash through my O. This is going to be the value of this 2-byte number. So what I'm going to do next is I'm going to show you on the programming calculator. This is on the Mac programming calculator. So if you're using a calculator, the programming calculator on the PC, it works a little differently. But actually the way it works on Mac is really cool. And you'll see how it shows exactly what we have here.
Hello. So I had to re-record this bit because I made a mistake the first time I did it. So I don't have the whiteboard anymore. I converted everything that was on the whiteboard into this Word document that you see up here. So, but it's the same thing represented, right? We got our 2 bytes. These are the place values up here for the bytes. And in fact, doing it as a table like this in Word is a pretty easy way to do it. Right, so for each of these, we had the value of each bit based on its place value. Add those up, you get the value of the byte. So this byte here is worth 154, this byte here is worth 186. But since this is the higher order byte, it's actually worth 256 times as much. So you multiply that out. This is the true value of this byte. Add it to the value of this byte, you get the value of the full number. So what I'm going to do up here, this is the programming calculator on Mac. It's a little different than the one on Windows, but the cool thing is whatever value you type in decimal or hexadecimal here, it shows you the byte values here the way you'd see them in a binary output on almost any kind of programming tool. It shows them in 4, just like in the TCP header and IP header diagrams. Excuse me. Right, notice it's the same exact way, right? It shows you 4-bit nibbles, and it gives you 1 byte, 2 bytes, 3 bytes, 4 bytes in each row. So just like the diagrams we had, this is the same type of output. So this will show you what those 2 bytes look like. So to represent 47,770, this is what the 2 bytes will look like: 10111010, which is just what we have here, and 1011010, which is exactly what we have here, which means we did the math correctly. So that wasn't all that hard, and when I showed you on the whiteboard, I did the math out longhand, which makes it take a little longer. But with just a regular calculator, basic calculator, you could do all this math really quick. Really, the only new skill you're really learning is to calculate the value of each byte, right, to get to this far. This is just plain old addition, and with a calculator, super easy. right? Then you need to remember that this second byte is worth 256 times as much. Calculate that. The rest of it's smooth sailing. So it's really not that difficult. Surprisingly, it's surprisingly simple. Excuse me. So if this whole thing is intimidating or scary to you, it shouldn't be. This is not that hard. It's something you can totally handle. So the next thing I'm going to do, though, I'm going to do another video here in a little bit. I'm going to show you how to calculate. This is how to calculate, right, a 2-byte value. And in the IP header, that's the most we have is 2-byte values. In the TCP header, we've got a couple 4-byte values. There's the ACK, the acknowledgement, and the sequence number. Those are 4-byte values, right? Because they're making these giant binary numbers because you're counting how many bytes are going back and forth in each conversation, and that can be a really big number. So those can be really, really big numbers. They get represented with 4 bytes. So we need to know how to calculate that too. You'd think it'd be 4 times as hard as this, but it really isn't. It's really only a little bit more work, and it's pretty easy to remember the technique. Once you see it, you'll say, oh, okay, yeah, I can see how that works. It's pretty straightforward. Once I show you, it'll be pretty self-explanatory. So, but I'm going to post this as the end of this video. I'm going to go ahead and post this one. That'll be a separate video that I'll get posted tomorrow.